Okay, number four, I mean, it seems like more of the same, but numbers three and four are leading us towards number five, which will help us determine where these two previous lines intersect. Right. So we have a parallel vector, which is the same as the displacement vector between 2 points. In this case, piece of one and p, or whatever piece of O and p. It doesn't make a difference. And here we're actually just given the 2 points, so we'll have to take it from scratch there. All right. So we actually have the points, so we're in good shape here. X, Y, Z. 3, 1, 4 plus t times -1, 6, -3. All right. So the second one, we just actually have to figure out the displacement vector first. So ABC. 5 minus 1, -2 minus 1, 7 minus 2, 4, -3, 5. Okay, so we'd be looking at x, y, z equal to 1, 1, 2 plus t times 4, -3, 5. And again, just a quick verification. Direction from one point to the other. Ideally, you go left to right, but if that were in a two-dimensional space, that would make perfect sense. But in the case of three dimensions, I mean, who really knows left to right, up to down to up, in to out, So just pick a point and go to the other as long as you're consistent, because whatever point is where your vector is pinned should be your starting point in your vector equation. Right? So just put in a 1 for t and see if that gives you your second point. So 1 plus 4 is 5. 2 plus 5 is 7. So it checks out, at least 2 out of the 3. All right, so now what we need to do is determine whether they intersect. All right, so we have a little bit of a kind of a quirky situation here. Kind of show you. Let me just reproduce the two equations down here, but I'm going to do them as I'll write them as separate equations. So I'm going to go purple. X equals 3 minus t. Y equals 1 plus 6t. X equals 1 plus 4t. Now, we're going to make a slight adjustment to this because what we're dealing with here, I mean, we have three equations, two variables. It seems like it's very easy to solve the value of t. What that would give us is a location of where these two lines would potentially intersect. Right? Now, we want to determine, well, it depends on the situation, I guess. As the graphs are being plotted, so there's two ways we could look at it. One would be whether or not the paths themselves intersect. That would be the case where t, give me a t for this value, for this equation, this set of equations that allows x, y, and z to be equal to the x, y, and z values to this equation for a particular t. Right? So that would show us whether or not the paths intersect. The other possibility is whether or not the points would collide as you drew them. Right. So one would be the intersection of the curves or the lines themselves. The other would be the intersection in motion. Right. So we could actually find it both ways. Actually, that's what we'll do. So one way would be if I had an infinite extension of xy, or the line related to these three equations, and the line related to these three equations. So extend it out infinitely. So think road, right? And then this road. Do they intersect? Yes or no? The other possibility would be two cars traveling down the road, possibly approaching an intersection, or two planes flying through the air, on the same plane. So they're at the same height, their paths are going to intersect, but will they intersect at the same time, causing a collision? So obviously benefits to knowing the solution in both cases. Right? So in the first case, let's just do this. 3 minus t equals 1 plus 4t. And then all right, so then we would just have to test that out for the other equations to see if they would actually cause an intersection. I guess I could do it by hand, I just don't want to. Oh, actually, yeah, just times 0.4. So we get a little contradiction here. So the value of t that makes x values equal leads to y values being unequal. Oh, wrong thing. I'm just double checking. So I plugged in, because it was 0.4, right? So I plugged in 0.4 here, 0.4 here. We get two different y values. So we have the same x values but two different y values. So that's showing that there would be no intersection. So the paths do not cross. Yeah, we would need to get the same coordinate x, y, z for both lines in order for it to actually show the paths cross. Which makes this probably not the best problem in the world, because I thought I changed it. Because in order for them to actually collide, the paths would have to cross. But I'll show you the process anyway. Just so you have it. And then at some point I'll come up with a better example. All right, so we have x equals 3 minus t, y equals 1 plus 6t, z equals 4 minus 3t. And then we would have a new equation, or a new set of parametrics. X equals 1 plus 4s, or some other variable. Y equals 1 minus 3s. And z equals 2 plus 5s. All right, changing up the variables here, because we have that speed equals distance over time relationship, which means time is equal to distance over speed. What we would be allowing for is the idea that time could be operating on different levels here, because if the two objects are moving at different speeds, maybe they're traveling the same distance, but they're moving at two different speeds, then these two variables would take on different units, right? So maybe this is going at, a distance of 100 miles, but at 50 miles an hour, and this is 100 miles going at 70 miles an hour. So the units would necessarily be different, and therefore, if we allow both equations have the same independent variable, that's assuming that they're both operating on the same level. All right. So by changing the variable here, what we're doing is we're establishing that we can actually basically be working with different units of speed for this object versus that object. I'm just using speed loosely as an example, but it could be, in other contexts too. It's just defaulting to speed is kind of my MO because it's easy to kind of latch onto. And then what we can do, because we have a relationship here, that's poor. Go highlighter. Is I can take green, 3 minus t, and set it equal to 1 plus 4s. Then do the same thing with the other ones. 1 plus 6t equals 1 minus 3s. 4 minus 3t equals 2 plus 5s. Okay, so we'd have three equations with three variables. What this will allow us to do is determine whether there is a value of t for this set of equations and also a value of s for this set of equations that allows those two lines to intersect, particularly at the same location, at the same point. Right? So I'm going to get this in the proper form. So I want to be able to use matrix operations to do this. So I'm going to I'll bring the t over. So this is going to be 4s plus t equals 2. So I'm adding the t, subtracting the 1. Negative 3, no, positive 3s plus 6t equals 0. And then 5s plus 3t equals 2. Hopefully. All right, so I come up with my coefficient matrix. 4, 1, 3, 6, 5, 3. Actually, you know what? Let me stack them up first. I don't want to skip steps. I mean, we have three equations, two variables, so we should be, more than well off here. Yeah, I don't think we have to write it as a matrix equation. We can actually just go right to the augmented matrix now that I'm looking at it this way. The RF should be pretty easy. I think. Hopefully. I think I'm the only one that ever makes this mistake. Let's make sure. Okay, we're good. Quit. Math frac. Best friend. Oh, and snipping tool. Probably a better friend. Alright, so we're looking at so S equals 4 over 7. T equals -2/7. Alright, so that's given, okay, alright, yeah. I had a, one of many, it's a mini, we'll call it a mini brain cramp today. It's just that this, yeah, I called this part the collision. This would be if their paths intersect. The other part would be a collision. I'm just trying to make sure I'm thinking about this the right way. Because what this is allowing for is for at different moments throughout each of the points journey along this line to end up at the intersection. But since it does give an intersection, it shows that they are crossing. Or it gives a solution, so it shows that they are crossing. So there are values for one equation that would allow the x, y, and z to be equal to the values of the other equation. I can check it on GeoGebra in a second. But this one is showing that it wouldn't happen at the same time. So the moment in which the x values come into contact with one another, the y and z values would not be in contact with one another. Right, so it wasn't a bad problem. It was just me. But it's always me. Let me just GeoGebra to verify real quick, though. Let me just pause. I want to make sure that the. All right. So should I do it by points? No, I'll just put in the equations. Curve 3 minus t. One plus 6t. 4 minus 3t. Comma t. Comma -10 to 10. And I'll put an a of 2/5. And then also a of -2/7. All right. So then my second equation 1 plus 4s, so curve 1 plus 4s, comma 1 minus 3s, comma 2 plus 5s, comma s, comma negative 10 to, well, negative whatever to whatever. You want to go negative 100 to 100, that's fine too. All right, looks like they're crossing a B, which is what I put in. Okay, so let me put in, this would be curve B, lowercase, put in the 2/5. Yeah, okay. And then the 4/7 should put me right at B. B of 4/7. Yeah, same coordinates, point B and D, which is this location. All right. So let me restate this. So let's delete that. All right, so that means there would be no collision but do paths cross. Right. Yeah, because, okay. Yeah, this is just a recap. By setting these two equations equal to one another in their current form, it's allowing for the time to elapse in both equations at the same rate, right? So time t equals 0 means the same for the first equation as it does for the second equation, but it couldn't possibly be that way because they're not starting at the same location. All right, I mean, I guess it could possibly be that way under certain circumstances, but it's not likely to be that way, right? So the fact that we let t be the same in both cases would mean that they're either traveling at the same rate or they're traveling the same distance or some combination of the two, right? So what this would mean is that if we got equality across the board here, that they were either starting at the same location and traveling at the same speed and intersecting at the same location, or they were intersecting at the same location, originating at two different locations at two different speeds, which is highly unlikely. The other possibility would be that they're traveling their own distances at their own speeds, and they just need to get to that location at a particular moment in time. All right, and so this illustrates that, and it allows us to, for the circumstances for the S equation, which I'll call the S equation, that you'd have to have, if we're going in units of time, 4.7 seconds, 4.7 hours, 4/7 meters, whatever, that amount of time to elapse in order to get to that location. And this one would have to actually be going backward in time in order to get to that location. So it would show that their paths would intersect with one another, but they would not collide with one another, or at least unless it's actually going backward in time. Or you're working in a context in which the independent variable is not time, right? So if it's dependent on location, because we can parameterize with respect to any number of things, like arc length. So if you're working around like a helix or something in Calc 3, instead of going forwards around the helix, you might be going backwards around the helix. So it's possible that you could have a negative movement, right? So this shows that the paths would intersect, but not necessarily that they would collide with one another.